Welcome to my presentation on linked lists. Um, so basically, linked list is a linear data structure, um, much like an array, but the difference is that this one, each element also has an additional pointer that's uh, which points to the next element in the list. So the key properties of a linked list is that it's got a dynamic size, so it means it can grow as you add and remove. So that's the main difference between a linked list and an array. And then each node or each element is the part which holds the data and the one for the pointer to the next one. All right. So and it also has non-contiguous memory allocation. We'll look at that also in more detail. So here we're talking about the pointers. So it is a variable that stores the memory address of another variable, and it allows for direct access to data in memory, enabling efficient manipulation. So basically a pointer, it's like a reference or um, something that tells you where to find the next one. So like we said, the memory is non-contiguous, so it means the address of the other element can be in another part of the RAM, not necessarily the next one. So we need a reference to know how to find it. So that's why we use a pointer. So pointers are also used in linked lists and also in trees. Sorry. So any most of the data structures that are non-contiguous in memory, they use pointers. Right. So contiguous memory allocation is shown in the diagram. They refers to a method where all elements of a data structure, maybe like an array, occupy consecutive blocks of memory. So it just means where the other one ends, then the other one begins. Then non-contiguous memory allocation is where the individual elements may be in different parts, so they'll be linked together using pointers. Right, so in terms of linked lists, we've got singly linked lists, doubly linked lists, and circularly linked lists. So these links uh, are done by the pointer, right? So in a singly linked list, there is the data and then the next pointer. So there's a reference to the next node in the sequence. So the diagram there, the code there is showing how it will be declared there. And then the traversal is only one way, like from the head to the start. We're going to look at traversal in much more detail next. Then a doubly linked list, in addition to a pointer to the next one, it also has a pointer to the previous one. So this one, it also means you can traverse it from the tail up to the head. Then a circularly linked list is just a singly linked list, but that also has um, a pointer that points back to the first one, right? As you can see in the grid diagram there, if D were the last element, it also has a pointer to A, which is the head. Right, so that is just a diagram to illustrate the linked part of it. I hope it's clear. Right, so on operations for linked lists, we have insertions, deletions, and traversal, right? Traversal is the purpose of visiting each node in a linked list, right? So it's basically iterating through all the elements. So whatever action you are doing, if in traversal, it's you are visiting each and every node, right? Right. So in insertion, you basically have to create a new node and then set the pointer of the new node to the current head, right? That's insertion at the beginning. Then update the head pointer to point to the new node. So then that's done in O of 1 time. I'm sure that will also be covered when we do time complexity. So there is the code example there. So like you said, we create a new node, right, and then assign data to it, and then we link the new node to the old head that's using the pointer, right? So we'll now be having a new head. So the head is the first element in a linked list. I think I'd forgot to mention that. Um, so this is basically inserting at the beginning, right? So we set up a function for that, and then we can now then start adding. So each time you add something, a new element, that new element becomes the head because we are adding it at the beginning. Then deletion involves removing a node from a list, right? So we're going to show the example of deleting from the beginning, right? Deleting from the head. So the code example there. So there is the code example for deleting from the head. So what it basically does is you use the you create a temporary head, right? If you see the first line there, you create a temp, you declare a variable temp that points to the head, and then we also have a pointer to the previous one. That's the now pointer, right? And then basically what we do, would try to change the head and then free the old head. So each time you delete something, you have to free the memory that was manually free the memory that was allocated for that particular one, right? Um, and then we also use a while loop, right? That's going to check, um, search for the key and keep track of the previous node, right? So at the end, it results in the key being deleted there. Um, then traversal, so it's the purpose of visiting each node in the link is starting from the head and following the pointer until now is reached. Right, so we use a while loop there. So we're going to check the current node, right? So basically it starts from the head from the head element. So and then we also check if the pointer there is pointing to now, right? So as long as that condition is still true, we are going to keep going forward, right? So that means this one is going to break out when we reach the last element, break out of the loop. So this one is basically going to print every element in the list. Right, so in applications of linked lists, they basically use where we need dynamic memory management, right? So it's also used as the founding structure for data structures like stacks, queues, and trees. Um, Linked lists are also used to represent adjacency lists in graphs, which are memory efficient for sparse graphs, right? So sparse graphs are generally those which use linked lists as founding data structure, and then also have polynomial operations. They can be represented using linked lists, enabling easy addition, subtraction, and multiplication. And then they're also used for memory efficient sparse matrices. So linked list store only non-zero elements in sparse matrices, saving memory and improving efficiency. So I think one of the takeaway this is efficiency in terms of space, in terms of memory. Right, advantages, dynamic size. So these lists, like we said, they can grow and shrink dynamically as needed. So this allows for efficient memory usage. Then also have efficient insertions and deletions, because when we delete nodes, we do not require to shift elements like in an array. It involves changing pointers, which generally takes constant time, that's O of 1. So they do not have a predefined size limit. Since they do not have a fixed size, there is no need to specify, like in an array, you don't need to specify that this one is going to take this much data. So this is ideal when where the data may change in terms of size. Then memory utilization. Memory allocation happens on demand, with each node being allocated when required rather than allocating at once up front. So yeah, we've talked at length about the advantages on the memory. And then the disadvantages. So since it uses for each element, it also has a pointer, so that can incur some memory overhead there. So for each element, there also is an additional allocation for the pointer. So that results in basically higher memory there. And then sequential access. So like we talked about during traversal, we can only go in one direction, like for single linked list, and then um, unlike and arrays where you can just access an element directly using the index. So these linked lists don't have indexes, so you just have to traverse maybe from the head to the tail, or from the tail to the head, depending on whether it's a single or a doubly linked list. Then complexion in implementation. Um, I think, as you have seen, the code is a bit more complex than maybe when you're working with an array, because we need to handle pointers, we need to manually uh, delete memory that's not used. So this may result in memory leaks, right? If unused memory is not released. Then the cache performance issues, due to non-contiguous allocation of nodes scattered throughout memory locations. Um, this can lead to poor cache performance, affecting overall efficiency during traversal. So, yeah, so instead of just traversing through one block, the the traversal may need to go through different types of different blocks of memory. So for caching, that may not be ideal. And then here, just put a glossary of terms just to assist. These are basically the new terms that you may not have come across before. So yeah, I've come to the end of this presentation. The glossary of terms, I think people can always just go through them themselves. Thank you.